So this is the final lecture video for the Unit 2 material. It has to do with birth of stars. And so generally what we're going to talk about is how in different regions of space we can find different areas that are the birthing areas of stars. And basically what it is this idea that's out in these clouds of gas and dust in the ISM, that there's thicker regions. We can find regions called molecular clouds. And these regions are, first off, let's see if we can get this in here, molecular clouds. These are very large areas. And so when we say large, we're talking, 50 to 100 light years across, or even greater sometimes. So a huge amount of space. Remember, a light year is roughly about 6 trillion miles across. So it's a tremendously large region of space. They're very cool regions. They are maybe down to roughly the 50 Kelvin range, hundreds of degrees below 0 Fahrenheit. Remember that temperature measures relative, motion. It's really the average kinetic energy that something's made from. Kinetic energy, remember, is 1/2 times the mass of the object times the speed squared. So if it's low temperature, it's low speed. And so, very cool regions. So there's small motions, but not big motions. And these regions, static electricity and the fact that it's so extended and very low density, all these regions keep these from collapsing down. And so they basically just last for a long time. They're called molecular clouds because that means molecules of hydrogen and others show up. A molecule of hydrogen is actually H2. In other words, 2 atoms of hydrogen linked together in an electric way with their electrons, and that makes a molecule. And that happens when it's so dang cool. If it's hotter, they're moving faster and they can smack into one another and break apart. And so that's one reason why they're molecular clouds. Now, these clouds are primarily hydrogen and helium, and the trace elements from older stars that they basically mingle themselves into that interstellar medium of hydrogen and helium after those older stars have died, which we've talked about before. So, what happens? You get this cloud, this huge cloud, just sit there unless there's some type of stress. It's really a shock wave of some form. So how does the shock wave come through this? There's really 4 ways. One way is maybe there's a nearby large star that dies. Dies in a supernova explosion. So that's one way. You get this big shock wave from this big star dying in the most cataclysmic explosion we see in nature. And it utterly destroys a blue star. And that shock wave from that can shock that cloud. Or we might have nearby large blue stars born. And all that energy that streams away from that blue star basically can shock that cloud, this molecular cloud. Or we have different molecular clouds collide. So that can cause a shock wave. And the last one we have to explain. 4 is in the, there are natural shock waves in the arms of spiral galaxy. Like the Milky Way. So you have this central region of a spiral galaxy. Here's an arm, here's an arm, and these guys will naturally spin around. And as they spin, they basically, interact with the gas and dust that are out in space. It's kind of like if you put your hand out of a car and the car is driving outside the window. We've all done this. It's one of those things that humans seem to do. You put your hand out, you go like this, and the wind pulls, pushes your hand back, and so you get this action that, causes, a shock wave on your hand, kind of like what happens to the gas in this molecular cloud as those big arms spin around. So the shock wave is just as those arms spin very slowly over a long period of time, it kind of puts pressure on those clouds. So what happens when that occurs? Really, this is what kind of happens. What happens is that as the shot, the cloud has pressure placed upon it. It breaks up, and then within that we get cloud fragments that can form one or more stars. So let me show you this. I'll go ahead and erase this, and I'll show you what I mean. So here's our cloud right here, just sitting there, and then there's one of those shock waves that hit it. And so what happens, it kind of pressurizes it, pushes over, it gets more dense, breaks up into cloud fragments. And we'll just take one of these. And we'll simplify this because, basically, if you imagine these shock waves, if you ever seen anyone smoke, and I'm certain you don't, but if you do see anyone smoke, and they're wreathed around their head with the smoke of whatever they're smoking, if they blow on it, the smoke kind of flies away. And so when a shock wave hits this, it's kind of like that smoke. It kind of causes it to be moved over and break up into these cloud fragments right here. And these could be still quite large, maybe one or several light years across, and they can hold enough gas for, one or more stars and certainly planets. So we'll take one like our own, where one star formed out of a cloud fragment, and of course then planets. And so what happens is, I'm going to simplify this. And make it very spherical, like a ball shape. Now, it's never going to be like this. It's going to be kind of, all sorts of shape and kind of wreathing around and collapsing down on itself. But we simplify it to make it simple. Now, so we can understand it. It's moving around an axis right here, and it's denser. And because it's denser, the mass has been pressed in because of that shock on that cloud. That gravity can cause it to collapse. So the gravity collapses the cloud fragment. So what happens as it collapses? Well, gravity is pulling in all directions, wanting it to collapse. But there is a motion as it's been rotating around the axis, and so what happens is that rotation opposes the collapse. It's kind of like if I have a something on let's say on a tether or rope, and I'm swinging it around. That rope keeps whatever I'm swinging around from flying away, but it would like to fly away. So let's imagine this. Up here, it's not moving very far up at that very top. Down toward here is moving farther. If they're going together, this has to go farther than that does as it rotates around itself. And so there's more opposition down here than up there. So what's going to happen is it is more apt to collapse down from the top down and the bottom up, and less here. So we get basically more of a disc shape forming. But gravity still pulls most of the material toward the center. So the vast amount of the material falls right in the center. And that material right there basically is what will form the star. It has fallen in the center. And that could be 99.5% of all the material of that cloud fragment that falls into the central portion of that collapsing gas cloud. And that's why stars are primarily made of huge amounts of gas and dust. And so what we get then is a collapsing cloud of material into a disk. So it breaks out into a cloud frame, it collapses down. We get the central region right in here with a disk forming around it. Now it's in the disk region that we might get the planets forming. So planets, moons, asteroids, comets, all of those only make up about 0.5% of all the material that originally made that cloud fragment, that is. And so what we find then is, let me go ahead and erase this. We have the central region right here, and then we have a disk of material out here. The planets will eventually form out of, and also the asteroids and the comets and the moons and such. I'll let you read chapter 5 to look at the process that's undergoing. Up at a certain region, as this shines, this birthing star, it pushes all the light volatile atoms toward the outer regions of what will become the solar system. In other words, the light gases like hydrogen, helium, such, are pushed much further away because they're light, and that light's energy, energy coming from the sun or the birthing sun, is enough to shove all those lighter gases further away from that birthing star. And that's why the outer planets are primarily made from, large gaseous planets made from hydrogen and helium, and the compounds of hydrogen like ammonia or methane. Whereas the heavier atoms, such as rocks and rocky material and metallics, they're not pushed as easily, so a lot of that remains here. And so we see that the planets basically closer and form closer to this birthing star will be more rocky and more metallic. Now, because they're heavy and dense, they get shoved together and they make hard, rocky planets, but not very big planets. That's the terrestrials up here in this region. That's the Jovian giants. Has to do with all that pressure shining away. And so what happens? This whole process of this thing collapsing down is one of balance. So what happens is that gravity's pulling it in, wanting to collapse down, but the energy flows out. And we get this balance. Now, as more material falls into here, it maintains a balance, but it collapses down. More and more getting hotter. The whole process really is one of energy. Gravitational energy as it falls in is converted to kinetic energy as they're moving and falling inward, which as they fall inward, they eventually collide. It's kind of like this. As they're colliding, that energy of motion, like my hands moving back and forth, is converted to thermal energy. And that thermal energy begins to heat it. So it's one conversion after conversion after conversion. And that thermal energy heats the birthing star. So how does that heat? Well, first off, it slowly heats up the center region. So the outer regions will look quite cool at first, but then as it heats and it expands, it begins to heat this region, and it could be very bright. Even though it's quite cool on the outside, it's so big that the size of it would actually make it shine relatively brightly, but probably not in visible light, probably in infrared radiation. But it would produce a lot of shining, but it continues to collapse down, collapse down, collapse down, until finally it can really heat up the outer region so it shines brightly in visible light. So let's use the HR diagram to kind of describe the process that goes on when a star is born. So let me go ahead and let's walk through this. By the way, that balance of the gravity pulling in versus the energy flowing out, we've seen before with our sun, where what we said, what makes all stars relatively spherical and of a certain size is that thing we call hydrostatic equilibrium. We've seen this. Well, that balance of energy flowing out and the power of gravity pulling inward, that balancing of the two, is hydrostatic equilibrium. It starts, at the very beginning of the birth of these objects, these stars. Now, what do we see with this when I look at it on an HR diagram? So remember, on an HR diagram, here is surface temperature, and it gets, remember with the scale here, it gets hotter going to the left. And then on this axis is the brightness, and it gets brighter going up. And then we said that most stars, average normal stars, are on something called the main sequence, where what we said, the main sequence are stars that are producing energy by some form of a proton-proton chain. So what happens when a star begins to form? Well, it slowly and surely begins to heat the internal parts of this birthing star, eventually heating up the outer regions of that cloud collapsing. And if we could plot it, what we would see is that it'd be way out here, very dim and very cool. But as time goes on, it begins to move up at an angle, this birthing star, meaning that it's going to get brighter and it's also getting hotter. So together, both of those makes it go that way. So finally it reaches a point when all of a sudden it tips over. Something, it reaches a specific value in all of this and how it's heating that it changes radically. So let's imagine what's going on here. right here, it looks kind of like a knee of a leg, a knee area. So this knee right here in this plot is known at the beginning right there as the T Tauri stage. And at this point, the surface becomes very violent. And so it would, it throw material into surrounding space off the surface of this birthing star. It's kind of like it's really starting the labor of birth. And it starts something called the protostar stage. And that's kind of like the point where the star is being born. Protostar stage. And that's right here. So what happens is, number one, it gets dimmer, but it gets hotter right there. So it gets dimmer going down, but it gets hotter. So this thing all of a sudden drastically collapses. Because it collapses in size, it gets dimmer, but because it collapses in size, it gets hotter. Because more gravity energy is converted to kinetic energy, which is converted to thermal energy, which heats it up. And so it goes through this. And it collapses until right there, something amazing happens. And at this point, the core reaches 10 million Kelvin. And if you remember, that is the temperature necessary for the to sustain the proton-proton process, proton-proton chain. Thermonuclear reactions start there. And this is where a star is born. So at that point, the core, right in the center of the core, it's gotten at the right temperature so it sustains this. So imagine what happens then. Is being heated up to now basically from gravitational energy. It's getting hotter and hotter and hotter as it collapses down, heats up the outer region. It all of a sudden collapses down pretty quickly and heats up that much more quickly down on the core of this, until finally what happens is that a lot more energy is formed in the core from this thermonuclear process. Now, all the way throughout this, there's been this balance of energy flowing out and gravity pulling in. But what happens as it's collapsing down in that protostar stage, and all of a sudden the energy increases tremendously flowing out, that shoves the star further out. It enlarges it. And it'll go too far, then it can be collapsed back down by gravity. So it goes through this little process of stabilizing. And for a star like ours, the core stabilizes roughly 15 million Kelvin, and then it becomes relatively stable. So what happens then is this thing kind of hops around and then hops on to the main sequence. Right there. It's a normal star. It's a little brighter, maybe a little hotter on the outside, but it's stable and it's become a main sequence star. Notice something. First off, on this, if you notice, it forms, as it forms into a star, it's still not on the main sequence. Has to stabilize, and then it hops on to the main sequence. So remember, there's two ways that a star is not on the main sequence. Not on the main sequence is being born or is dying. We'll talk about that in Unit 3. So as it is birthed here, it's not on the main sequence, and then it stabilizes and goes on. Now, there's a couple of things to note about this. You see this, where star hops onto it. You know, it takes a little bit to stabilize there. And if I look at this, what we find is stars basically follow the same process. And so where they fall onto this, where a star ends on the main sequence is the mass. It's all to do with mass. A small star will come up and end on down here. A large star will come down, end right there. Medium-sized star like ours will end there. So there's a couple of things. Make sure you get this. This is key. Number one, I'll say it again. Where a star ends up on the main sequence depends upon the mass. Where a star ends on the main sequence depends on the mass of this birthing star. Once it's on the main sequence, get this down. Once it's on the main sequence, it doesn't move up or down the main sequence. How can a small star, very low mass star, become a big mass star by itself? Can't do it. How can a big star by itself become a small star? Same thing true with the intermediate. How can it become big or small by itself? It can't. So where a star ends up on the main sequence is regarding its mass, and where it goes to the main sequence is where it stays the whole length of time as a main sequence star. And just take one last thing, all stars end up on the main sequence for the vast majority of their lives. And so that's where they stay. They do not move up or down the main sequence, any particular star. They stay right where they are. And so once they become a main sequence star, they're just normal average stars. They stay there for the vast amount of their lives until one thing happens. Turns out that the fuel in the core is used up, because remember on the proton chain what we said? We said that 4 hydrogen atoms combine together in a thermonuclear process to form 1 helium atom. The protons, which are hydrogen atoms, is the fuel of the proton-proton chain. Helium is not a fuel in the proton-proton chain. And so it becomes inert while the core is at lower temperatures. So we use up fuel over time and lock it into helium, and therefore we don't have the fuel necessary to maintain that hydrostatic equilibrium. You know, energy flowing out from the proton-proton chain, gravity pulling in, and once we lose the fuel, less energy is flowing out, and all of a sudden gravity, that force that's always there, can start a change in this star to basically force it into a dying star. Still a star, but a changing star because of this change in the hydrostatic equilibrium as the fuel is used up. And that's what we'll talk a lot about in Unit 3 on the death of stars. So this is primarily the process the stars follow as they're born. So this is the last video for Unit 2. Make certain you have a chance to look at this. I'll put out an email to everyone to let you know that it's here. And guys, we got an exam this week, so be prepared for it. Make sure your study guide 2 is finished. And I will see you during those exams. Talk with you soon, guys. Take care.